So this is a paper about trading networks. So as economists or computer scientists, we can think about many kinds of markets where you sort of have a network structure. Think about markets for manufactured goods, where different firms are providing different inputs and outputs to each other, and they're sort of arranged in a network. Think about two-sided buyer-seller markets that you would like to study if you are an industrial organization. Or think about matching markets, labor markets, matching, and so on. You can also think of them as sort of bipartite graphs, where you have some trading relations between workers and firms and so on. Okay? So networks or network markets, you can think of many sort of different kind of models that capture some of the stylized facts about those kind of markets. So one approach, which is sort of coming from almost this EC community, is we start with sort of the techniques and apparatus of two-sided matching markets, and then we try to generalize the results that we have in this literature about certain nice properties of the set of stable matchings and certain kinds of mechanism design issues in those matching markets, and we try to generalize it to networks. And there was a nice stream of papers in recent decades, and many of them were actually presented at EC, which try to do this exercise of generalizing from two-sided matching markets to networks. Okay. So I am concerned. So I'm concerned about networks, and I'm concerned about networks where we also have transfers between the different parties in the transaction on the network. So different firms pay transfers to each other. And if you have transfers, so one sort of natural first thing to do is you start with quasi-linear preferences, transferable utility, and this makes somehow stuff a bit simpler. But of course, in many kind of realistic situations, transferable utility or quasi-linear utility might not be the most realistic thing. So natural way of sort of coming into a situation where you don't have quasi-linear preferences, for example, is if you have certain kind of natural frictions. Think about transaction taxes in those networks. Think about sort of bargaining costs or these kind of things. Or you just don't have this kind of quasi-linear preferences and transfers, maybe. Okay? So in this paper, I'm studying trading networks with preferences that are not quasi-linear. I'm not the first. So last EC, there were two very nice papers. Sort of my paper is a follow-up to this paper in some sense. So there was this, Ravi presented, it's Fleiner and co-authors presented this paper where they generalized the trading network model and show existence of equilibria in those models and sort of equivalence, core equivalence kind of results for the trading networks with non-quasi-linear preferences. And there was a paper by John Hadfield, Scott has presented that last EC, where they considered also a model of trading networks with non-quasi-linear preferences, where they showed the equivalence of certain kinds of stability concepts. So this paper somehow fits nicely into what has been presented in the last EC. What do? I provide a bunch of structural results for trading networks with non-quasi-linear preferences. So I prove results that are sort of generalizations from results that you would know from the matching literature. I show sort of a lattice theorem. I show that the set of competitive equilibria in these markets, they form a lattice under some assumption on preferences. I provide some generalization of rural hospital theorem. And once you have those kinds of theorems, then you can also think about, maybe in a limited way, about mechanism design in these kind of markets. So I have some partial incentive compatibility results for certain kinds of agents in these kind of networks. Okay? If you don't like networks, those results are new for matching markets already. So in this generality, because I have non-quasi-linear preferences on both sides of the markets. It's already new if you like exchange economies with indivisible goods combinatorial demand and don't like quasi-linear preferences. Sort of in those environments, it's already new, but I show this in a network setting. Okay, that's what I'm doing. There's a lot of literature. And here's a model. Okay, so this is a model. It's sort of a generalization of this Hatfield and co-author co-author paper from 2013. So you have firms. Agents are called firms. And they are arranged in sort of this directed graph. So you have firms, and then you have something called traits. So those are directed edges between firms. And the direction of that edge will tell you who is buying something and who is selling something in this potential trading relations. So those are potential trading relations, those traits. Okay. So just a directed graph is sort of the structure that you have there. Okay. And you can, it doesn't have to be acyclic. You can buy and sell sort of in cycles if you want. Just you have a directed graph as sort of a basic ingredients. Okay. And then you want to have a model where certain kinds of those traits form. And not only that, but you also have transfers. So, the different firms agree with different traits with each other. Firm can sign multiple traits with different firms, with the same firm, and so on. And transfers or prices are agreed upon for each potential trait. So each trait has a price, and this is you can think of it as a transfer that is, for example, paid by the buyer to the seller of the service or the good that is involved in that. Okay. Now here's a sort of, this is about the general preferences. What I'm doing here is I'm making only very mild assumptions on utility functions. Okay. So it's not quasi-linear. The only thing that I do is, so each of those firms, they have utility functions, and they evaluate different combinations of traits together with different kinds of transfer vectors. So you have utility for a set of traits that they're involved in, and a vector of prices or transfers that are attached to those traits. And the only assumptions that I make is a continuity assumption. So this utility function for each firm is continuous in prices. Okay, so in the second argument. And it is monotonic. So you like to have, if you're selling something, you like to have a higher price. And if you're buying something, you would like to have a lower price. Okay, so it's monotonic and continuous. All right, that is a model. There is a possibility to sort of having certain kinds of traits to be totally infeasible, and this is captured by this minus infinity. You can attach to a certain set of traits, you can attach a utility of minus infinity, which basically just tells us, okay, it's not possible to execute those traits with each other. Okay, so that's a model. Okay. And then you have a notion of equilibrium, which is just a competitive equilibrium. So you start with your utility function as a firm, and given some price vectors, so each trait, each potential trait in this economy has a price attached to it. Firm is looking at this price and maximizing utility, and this gives you the demand. So it demands a bundle of trait, that firm. Could be, in general, that some price vectors, you always have some price vectors where the demand is multivalued. So you have some price vectors where multiple combinations of traits are optimal. You're indifferent between all of them. Okay? So in general, it's a demand correspondence. Then you have the notion of competitive equilibrium, which just says that the market is clearing. So you have a combination of a price vector. Each trait in this network has a price attached to it. And some of those traits are actually realized. All of the traits have a price. Some of them are realized. And what we are requiring is that for each firm, a set of traits that are realized for that firm are actually demanded under those prices. Okay? So it's just a competitive equilibrium notion. So you might be wondering, so you have this sort of very thin market with a lot of heterogeneity in firms and different trading relations. Why would you assume price tanking behavior? You can give it a sort of a very nice cooperative foundation under certain kinds of assumption and preferences that was done in the Fleiner et al. Paper last year. So you can give it sort of a competitive equilibrium. There's certain kind of equivalence between those and some notion of which is generalizing pairwise stability for matching markets. Okay, so if you're worried about that, but I'm working with competitive equilibrium sort of because it's, I think, the right sort of space to operate in if you want to prove the kind of theorems that I want to prove. Okay, you have to put certain kind of restrictions on preferences. This is sort of the notion of substitutability that the literature has agreed upon, and it fills an entire slide. But it's sort of, you outrule certain kinds of complementarities between certain kinds of traits, or you want to have certain kinds of complementarities between certain kinds of traits. So it consists of two parts. You have this thing called same-side substitutability. If I'm buying something and I'm having different buying contracts to consider, I want to basically outrule with this preference condition that there are two complementarities between different buying, two strong complementarities between different kind of buying contracts. So I don't want to have that. And if I'm selling the same, if there are two different selling contracts, there shouldn't be too much of complementarity, that I only want to sell those two things together, but not each of them separately. Okay? Cross-site complementarity tells you something about how I consider trades where I'm buying something together with a trade where I'm selling something, and we basically want to have some form of complementarity between upstream and downstream trades. Okay? Geometrically, it looks like this. Same-side substitutability, left-hand side picture is a same-side substitutable. Do I have a pointer? Probably not. No. So it says, okay, you do a monotone price change. I increase the price of one contract. Maybe I'm down here in that corner. Can I go down? Okay. I increase the price of the first trade, right? I've consumed so far both trades. I increase the price of the first trade. What shouldn't happen that is that I should suddenly decrease my demand for the second trade. And indeed, here I still demand that trade. Here is not good if you go from here to here. You drop the second trade, even though you only have changed the price of the first trade. Okay? Cross-site complementarity looks like this geometrically, and now I have 5 minutes to show you all the. There are two monotonicity conditions that I put on top of that. Okay, law of aggregate demand, which tells you something about the number of contracts that I'm signing upstream and downstream if I react to a monotone price change, and the law of aggregate supply, which is a monotone price change in the other direction. I need those, but they're a bit milder than the previous ones. And if I have them, I have a theorem. Okay, that's the main theorem of this paper. So we have the set of equilibrium prices is a lattice. It's not only a lattice; it is a sublattice of Rn or R omega. Okay, so take two price vectors. Takes the pairwise maximum of each of the prices for the different trades. The vector consisting of the pairwise maxima is a competitive equilibrium price vector, and the same if you take the pairwise minimum. Okay. Second part of the theorem tells you something which can be interpreted as a generalization of the rural hospital theorems. It tells you modulo indifferences, basically. You always, the following is an invariant in all equilibria, competitive equilibria. The number of buy contracts that I'm assigning minus the number of sell contracts that I'm signing. Again, there's some issues with indifferences, but modulo indifferences, this is the theorem. Okay. Right. Okay, so this theorem is well known in the quasi-linear context or in other kinds of contexts. So what is sort of a bit challenging and which requires some heavy lifting is that sort of standard proof techniques don't really apply in this environment that I'm considering. So one very standard way of proving such a theorem is you go via Tarski's fixed point theorem, but then I have to work with correspondences, and there is not the right kind of Tarski fixed point theorem for correspondences available. There's, on the other hand, there's this very nice duality approach, which was also presented in an EC paper, where you basically look at the duality between welfare maximizing assignments and competitive prizes in some sense. This also breaks down, first of all, because my competitive equilibria, they could be inefficient in some circumstances, and also the convexity of the set of competitive equilibria fails. Sort of, sometimes you don't even have a connected set of competitive equilibria, so you can't use this kind of duality theory. So you have to involve, you have to engage with tie breaking. That is sort of the thing that you have to do. And I don't have the time to show you how to break ties, but you can do it. But what I want to highlight is that sort of all the assumptions on preferences that I make are somehow necessary, because otherwise my tie breaking doesn't work, and otherwise I have counterexamples. The law of aggregate demand, the law of aggregate supply I need, and full substitutability, you have to have the right definition. It's important to define it in the right way on prices where demand is multivalued. So you have to get the right one. Okay. Otherwise, you can also have counterexamples. All right. I have to wrap up. Put more structure on preferences. You can get the existence of sort of extremal equilibrium. Right? In general, with only a full substitutability, law of aggregate demand and law of aggregate supply, I get the lattice result, but the lattice could be empty, it could be unbounded, stuff like that. You have to put more structure on it. But once you do that, you can have a compact set of equilibria, and you can find a terminal Bayer optimal, terminal Seller optimal point in the set of equilibria. Okay. And once you have those extremal equilibria, you can do some limited form of mechanism design. And here is the theorem, which is telling you that if there happen to be agents which are terminal buyers, so they only want to buy, they don't want to sell, right? And moreover, they only have unit demand, they don't want to demand multiple things. If you know that, we can implement in a group strategy proof way for those kind of agents a competitive equilibrium, which is the terminal Bayer optimal equilibrium, okay? Which is sort of the appropriate generalization of the statement that the worker optimal matching can be implemented in the Kelso-Crawford economy, for example. All right, time is up. Here are some questions I couldn't answer. Please answer them. And otherwise, that's all.